Let's talk today about the move structure, which is a good structure to talk about as a follow-up to talking about the R index, which we just covered in some previous videos. So in this video, I'm going to motivate it and I'm going to actually show you what the structure looks like, or at least an initial version of what the structure looks like. And let me first of all show you the paper. This is a recent paper. It was published in iCalp in 2021, which is a computer science conference by two researchers at Riken in Japan. And those are Takaki Nishimoto and Yasuo Tabe. So at the end of the previous R-index video, we talked about the locate query, and once we had finished discussing all the data structures that made up the data structures needed for the locate query, and then combined them with the data structures that were needed for the match query, we ended up with bounds that kind of matched this row from this table, which I've extracted from the paper that describes the R-index. So that's the one that we discussed. There's other rows here. You'll see that they kind of provide other trade-offs. But none of these trade-offs are what you might call best of both worlds with respect to space and time. And that's really the first kind of motivation for this move structure, data structure. Right? What the authors of that paper observed was the R-index is great and all, and it's fantastic that it achieves big O of R space and a reasonable time bound. But wouldn't we love to be able to do big O of M plus oak time? That's in some sense the best we could possibly hope to do, given that we have to do the matching query, which means we have to look at all M characters of our pattern, and given that we have to do the locate queries, which means we have to do oak locate queries. So what if we could have big O of M plus oak time and big O of R space? That combination isn't achievable with R-index. Instead, you have to make a trade, and you can make it in one direction, where you get the sort of ideal big O of M plus oak time, or in the other direction, where you get the ideal big O of R space, but you can't achieve both. If you want big O of M plus oak time, the space is mildly worse than big O of R, right? It's big O of R times a log-log factor. And if you want big O of R space, the time is mildly worse than M plus oak, because you have to multiply, again, you have to multiply in a log-log factor. Can we have best of both worlds instead? This is sort of one of the motivating questions of the move structure. Here's another motivation for the move structure, and this one is not really one that the authors of the paper were considering, but it's another important reason why, in practice, the move structure can be a useful replacement for the R-index. And this really has more to do with sort of pure computational efficiency and how computers work than it does with any theoretical bound. The R-index, as we've seen in other videos in this series, it really consists of a lot of separate data structures, right? So just talking about the locate queries, right, we have those predecessor data structures we were talking about. But forgetting for a moment about the locate queries, just looking at the match queries, we have things like bit vectors and wavelet trees. And recall that wavelet trees are themselves made of bit vectors. And if we have wavelet trees and bit vectors, we need to be able to support queries over those wavelet trees and bit vectors, so rank queries, sometimes select queries, access queries. And those in turn require more data structures, right? We had a discussion of Jacobson's rank and Clark's select. And in order to be able to do those constant time rank and select queries, we need supplementary tables of various kinds, right? The Jacobson's rank data structures, we had something like 3 extra tables that we had to build and query. And then Clark's select, we had even more. I think we had 5. So we have all these disparate data structures, separate data structures. And over the course of one query, like even just one round of the matching query, we have to go access many of them, sort of touch them in lots of different places to access different bits of memory to get the answer to our query. This is not so good from a computational efficiency perspective because it has what we would call poor locality of reference. We have to jump all over memory and piece together information from different places in memory that are not necessarily near to each other and are not necessarily predictable, right, based on previous memory accesses. And when you have a memory access pattern like that, you're forcing the memory infrastructure to go retrieve things from main memory for you and bring them back close to the processor. And there's a delay associated with that. There's a kind of pause on the order of 100 nanoseconds or so. Doesn't sound like a lot, but that can be very significant, especially if you're incurring that penalty over and over and over again. And another name for this penalty is a cache miss. In other words, if you're accessing a memory location and it's not one that you've accessed recently, then chances are you haven't kept that chunk of memory in your cache close to the processor, so you have to go retrieve it from main memory. So this is another complaint about R indexes. Because they're made of such disparate collections of structures, because even a single query requires that you go access those structures in several places, it tends to have poor locality of reference, which just makes it slower than you would perhaps hope. So in comes the move structure. And so let's discuss the move structure. And the move structure is another Burroughs-Wheeler based data structure, right? The move structure is very closely related to the R index. In fact, as we'll see, in a sense, it's like a rearranged version of the R index, right? So it's going to be a full text index. It's going to be based on the Burroughs-Wheeler transform. It's going to do the same sorts of queries as the R index, but the structure itself is quite different. It's different in one sense because it's not arranged anything like the R index, but it's similar in another because you could say, well, it's just a rearranged R index. You can see it either way. Okay, but to go back and remember a principle that we laid out at the beginning of when we studied the R index, we said that when the text that we are indexing is repetitive, this might be the case, for example, if we're indexing a pan-genome, a collection of, say, human genomes, and any two human genomes are extremely similar. So if we're indexing, let's say, dozens or hundreds of human genomes, that's very repetitive. When our text is repetitive, then the Burroughs-Wheeler of the text tends to consist of long equal letter runs, like my row your boat example. I've been using this as a running example. I'll continue to do that in this lecture. So as you can see, after the Burroughs-Wheeler transform, we tend to have these stretches of like all these W's in a row, all these R's in a row, all these O's in a row, all these spaces in a row. So that's a feature that we know the BWT has, and that's useful for compression, and it's useful for compressed indexing. We've already seen this. Another thing that's runny, we've also sort of seen this in our discussion of the R index and its locate query, but let's just look at it again here, is that the LF mapping is also runny. Right, so very early on discussing the Burroughs-Wheeler transform, we talked about the LF mapping. The ith occurrence of a character in the last column of the Burroughs-Wheeler matrix corresponds to the same text occurrence as the ith occurrence of that character in the first column of the Burroughs-Wheeler matrix. Okay? That relationship, when the input text is repetitive, that LF relationship, the LF mapping, is runny. Okay? This is my term, not other people don't use this term runny. But anyway, the LF mapping is runny in the sense that if you look at runs in L of a particular letter, right, L being the last column of the Burroughs-Wheeler matrix, in other words, the Burroughs-Wheeler transform. So the thing labeled L here is the Burroughs-Wheeler transform. It is called L because it's the last column of the Burroughs-Wheeler matrix. If you have two adjacent positions in L that have equal letters, this is saying equal letters, then the LF mapping is going to take those two positions to adjacent positions, right? So if the positions are adjacent and equal letter to begin with, then if you take the LF mapping of one and you take the LF mapping of the other, they will be adjacent at the destination, right? The LF mapping maps these to some other place, to their image. In the image, they are next to each other. After the permutation, they are still next to each other. Okay, so two positions that are in the same BWT run are going to move through the LF mapping in a parallel fashion. And I like to sort of picture this either with arrows like this, So R, 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 those three R's over there in L, they're all right next to each other. And their LF mappings take them here, right? These are the first three R's in the last column of the Burrows-Wheeler matrix. These are the first three R's in the first column of the Burrows-Wheeler matrix. So the LF mapping takes those to those. It takes these to these. And I will summarize away kind of all these different arrows sometimes by just drawing a parallelogram. All right, so the parallelogram is like saying, well, all these things are part of the same equal letter run. So the LF mapping is, as a block in a way, is going to kind of like block permute them to a particular block of letters in the first column. Okay, so this is what I mean when I say the LF mapping is runny. The LF mapping takes letters that are in the same equal letter run in L, and in a block, sort of together and in parallel, it maps them to a consecutive stretch of letters in F. Okay? And recall, we use this in the locate query for the R index. You can go back to previous videos to remember that. So I could picture all of these relationships, all of these kind of runny LF relationships this way by drawing a parallelogram that connects all the maximal equal letter runs in L to their destinations in F, right? The LF mapping would map, for example, this stretch of three R's that we were just looking at along this parallelogram. Hopefully you can see the one I'm highlighting to this three stretch of R's. And so if we just write out all those relationships, draw all those parallelograms, it looks like this. Okay? The move structure, which we're about to discuss, is a data structure that specializes in exactly these kinds of permutations. It specializes in representing and executing permutations that are runny. Right? So that's what the move structure is really for. And since the LF mapping is an example of one of those permutations, the LF mapping is a perfect kind of function to apply the move structure to, and that's what we're gonna do first here. And the move structure does achieve, with maybe the slightest asterisk, which we'll come back to later, the best of both worlds bounds, which is to move through this permutation once requires only constant time. All right. So I didn't write out the big O of M plus oak because we have to do several things, but just in one step of using the move structure, executing one LF mapping or one permutation, that takes constant time. And the data structure that allows us to do this is big O of R space, just like with the R index. Remember, the R index could not achieve this. It couldn't achieve both at the same time. If you decided you wanted big O of R space, you had to pay a mildly worse than constant query time. And if you wanted constant query time, you had to pay a mildly worse than R scaling factor for the space. Okay. What is this thing? How do we actually write down a move structure? Okay, well, let's do it. And the move structure is going to, in some sense, just be representing exactly those parallelograms, right, that I wrote on a previous slide, plus some useful information. Okay, so let's do that. So step one is, here's our L and our F, just like we were showing on the previous slides. We know that we can think of the LF mapping as sort of parallelograms connecting the runs of L to their counterpart runs in F. But let's just start by making a bit vector, which we call P, which is parallel to L. And P is going to have a 1 everywhere where there's a run head in L, right? In other words, for every run in L, here's a run, here's a run, here's a run. Every run has a head, right? Every run has a first letter in the run. Boop, boop. These are all run heads. So we mark all those with 1s in the P bit vector, as you can see. Right? And everything that's not a run head remains 0. Okay? So that's our P bit vector. And we're going to make another bit vector Q. And Q is going to mark with a 1 the image of all the run heads in L. In other words, if you take that run head in L and push it through the permutation, right? Take its LF mapping, then we're going to mark its counterpart at the far end of the LF mapping. We're going to mark the position that it maps to via the LF mapping. And those are going to be marked in a separate bit vector called Q. So if you look at P and Q and you look at all the parallelograms on this slide, you'll see a relationship, right? Whenever there is a set bit in P, let's stick with this run of R's here. Wherever you have a set bit in P, like this one, what we did is we sort of followed it through its parallelogram, found its counterpart here, and marked that with a 1. All right? And we did that for all the runs, for all the ones. Right? The ones marking the run heads. Just let me pause for a moment and explain something important, which is Q is not marking the beginnings of the runs in F. That's not what it is, right? It's Q is really all about the opposite side of the permutation, but it is not about F really per se, right? So Q is not marking the run heads in F. I mean, it does mark them, but it marks other things too, right? Like these ones here are not, well, okay, sorry. This run here is not a run head with respect to this run of O's in F, right? So just remember, it's marking not the run heads in F, it's marking the image of the run heads in L, right? So it's taking the ones in the P bit vector, pushing them through the permutation, and then marking them at their destination. Okay? So P and Q are bit vectors, and I think it should be very clear. P and Q have R set bits each, right? Because for every run, we're setting 1 bit. Okay? So now, how do we actually sort of like do the permutation? And what is the move structure? So we're using it to represent a LF mapping permutation, but let's just forget that for a moment. It could be any permutation, right? The move structure is perfectly capable of representing any permutation. Doesn't have to be the LF mapping. So let's give the permutation just a more generic name rather than LF. Let's just call it pi, right? Pi for permutation. So we'll call the permutation pi. And so, for example, here I am drawing one parallelogram that's connecting a run here with its image here. You can see this run begins at offset 40, 1, 2, 3, 4, 5, 6, and it connects it to this beginning at 10, 11, 12, 13. So 46 to 13. So we would say pi of 46 equals 13. Right? If we take the offset 46, push it through this permutation, you can sort of visually imagine we're sliding along that parallelogram and we land on 13, offset 13. Likewise, for the two other offsets that are part of that run, 47 and 48, we land on adjacent positions, 14 and 15. So 46 goes to 13, 47 goes to 14, 48 goes to 15. I'm just getting you used to this notation of pi. Okay, I can tell you what the move structure is now. It's actually kind of simple. The move structure is an array of records, 1 per run in P, right? So if you picture P, remember P marks the run heads in L. So I could have also said run in L. P marks the run heads in L. P consists of sort of sections where it's like a 1 followed by several zeros before you get to the next one. You could consider that a P run. So that's like the way a run is represented in P is with a 1 followed by several zeros. Right? So what we're going to make is a move structure, which is a table, and it'll have a row for every run, for every P run. Okay? So 1 row per run at first. We'll refine that later. But anyway, 1 row per run at first. And each of these rows is going to contain 4 fields at first. We might add more fields later, but it's going to contain 4 fields. First of all, the offset of the run. So how far is this run from the beginning of P? The length of the run. So how many letters are actually part of this run? A field that we call pi, which is just pi of P. In other words, if you were to take the run head and put it through the permutation, what offset would you land at? Right? So pi is pi of p. It's pi of the run head. It is where the run head maps when it is put through the permutation. And then this final column, which we use this Greek letter to represent, this Greek letter can be pronounced different ways. I'm going to pronounce it xi. All right, so we have a column called xi, and xi is holding what I'm calling the ID of the p run that covers this offset. Right? So in other words, that pi field is where does my run head map as an offset? This is asking the question, which of the p runs is the run that contains that offset? Okay. So this is probably best understood through pictures. So we will definitely see pictures to illustrate each of these fields. So let's begin at the beginning. Let's start to build a move data structure by making one row for every p run. And so we're going to begin at the very first p run, right? So all the way over here. First p run's very simple because it's only got one letter in it. So we'll start with this p run and we'll start to enter it into our table. So here we are. This is run ID 0. We're going to do all our numbering starting at 0. So this run has ID 0. It is at offset 0. It has length 1. Okay, now we want to fill in pi and xi. So for pi, we need to remember, well, where does that map? Like, where does the permutation, where does the LF mapping take the letter at offset 0? Okay, well, let's just bring back the picture and say, okay, all right, well, I've highlighted this parallelogram because this is the one for the run we care about, right? The run we're currently looking at is just the run consisting of that one t. And as we look at this parallelogram, we can see it's mapping it here. So the answer is this offset, whatever that offset is. So let's come back and we can see from this picture it's offset 46. Okay? So that run, its head, the run is length 1. So I guess the run head is the entire run. But anyway, that run's head maps to offset 46. So we put 46 here. Okay, now for xi. Xi is maybe the trickiest of these to figure out what it should actually be. And so to compute xi, we're going to go to that offset 46 where we mapped. We're just going to look up here, back in the p bit vector at that offset. And we're going to ask, okay, which is the run that contains this offset? We can sort of see, just looking up there, we can see it's going to be this run right here, right? That's the run that contains this offset. But we need to report its ID, right? So like if the first run, this one has ID 0, and this run has ID 1, and this run has ID 2, etc., which run is this one, the one that covers offset 46? Well, if we count them all out, the answer is 12. That's the run ID 12. So we stick 12 in the xi field of our move structure. Okay, well, that's the first row. Great. Let's do the second row. All right, this one's like slightly more interesting because it has more than one letter in it. All right, so this is run ID 1. It is at offset 1, right? Offset 1. It has length 3. Okay, pi takes it to offset 34. I just went to the parallelograms and picked the right one and put it on my picture so that you can see the permutation takes offset 1 to offset 34. And so this run maps to this part of the q-bit vector. Okay, the final question is which of the runs is the one that contains offset 34? So we can count them off and we can see that it's run 8. Right, so we put 8 here. Boop. Okay, we've done 2 rows. Onto the third row. I went ahead and did all the work. The third row is actually kind of interesting, so let's pause and look at this, right? So the third run, okay, it's at offset 4, okay, it has length 9, okay. The permutation takes its head to offset 52. Great, so far so good. But now this question of what's the ID of the run that contains offset 52? Notice that offset 52 is not a run head. It's in the middle. It's in the middle of a run. That's fine. Doesn't matter. It's definitely in a run. It doesn't matter if it's the run head or in the middle of the run or if it's the run tail or what. We just still want to record what's the ID of the run that contains offset 52, and so the answer is 13. Okay, let's do the next one. Now we're at offset 13. Meant to use this. Now we're at offset 13. It has length 3. It maps here to offset 19. Offset 19 is in run 5, etc. Blah, 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 blah. We can keep doing this over and over and over again. And we are constructing all the rows of this table here. Okay? This is you might call it like the first draft of the move structure. This definitely embodies what the move structure is. We are going to change it slightly, but only slightly. So you already have a very good feel for what the move structure actually is. Furthermore, I think it's pretty clear this is a big O of R data structure. After all, it has exactly R rows in it, right? One row per run. And each row consists of 4 numbers, right? P, L, pi, xi. So it's pretty easy to argue this is a big O of R data structure. You might say it's big O of R words because it's 4 words per row. Okay. However, we don't know yet how to use this thing, and we have not yet proved that we can achieve that best of both worlds result, the result that says one iteration of our matching query, for example, is constant time, but the data structure is still big O of R space. Okay, it's clear that it's big O of R space, so I guess we've kind of done that part. But it needs to still be the case. Once we've described how to do constant time queries, it has to be still the case that the data structure is big O of R space. And doing constant time queries, as you'll see, requires some modifications. So it has to still be big O of R after those modifications. So that's what we'll get to in the following videos.